Alrighty, good afternoon, everyone. Carahsoft Technology would like to welcome you to our Google Cloud and MLtwist webinar, Navigating AI Data Complexity with Sandia National Laboratories. At this time, I would like to introduce our speakers for today. David Smith, founder and CEO of MLtwist. Andrew Cox, R&D System Analysis at Sandia National Laboratories. And Stephen Bussell, Customer Engineer for Google Public Sector. Andrew, the floor is all yours.
Thanks for y'all being here. What we're going to talk about today is how Sandia National Labs has been supporting TSA, the folks that screen you at the airport, to develop machine learning algorithms that can help better detect threats. And so we're gonna get into that. But first, I'd like to tell you a little bit about Sandia National Labs. We are. Oh, excuse me. Let me tell you a little bit more about the problem that we're trying to solve first. Thank you, David. So TSA, of course, wants to be able to detect when threats go through or when someone attempts to have a threat go through the checkpoint. So, for example, if someone wants to bring on a gun or a knife or something like that, you put your baggage through an X-ray or you go through one of the body scanners, and they have algorithms that will detect that stuff. Of course, TSA has an interest in always continuing to improve that. In recent years, TSA has adopted an open architecture strategy, which means that in addition to fielding algorithms from the companies that provide the X-rays and the body scanners, they want to be able to build on that and draw from the broader machine learning community and a broader set of market players to add additional algorithms to maybe specialize, to do better, and to sort of continuously improve. And the idea is that TSA wants to be able to get algorithms out there a lot quicker and make those algorithms better so that so that passengers can get through much more quickly and much more secure. A big part of that, as many of you know, is if you're doing any sort of machine learning, you have to have a really robust, quick data pipeline. And so what we're going to talk a little bit about today is how we stood up that pipeline for TSA, but we did the sort of initial version and lots of growing pains in that. And we're going to talk about how we matured that, certainly with the help of MLtwist, who is one of the other partners on this call. Next, please, David. The first thing, before we get into the specifics, I just want to tell you a little bit about Sandia National Labs. We're a national lab, one of the national security labs that does R&D for national security items. It includes nuclear weapons and then all sorts of other stuff, obviously, including X-ray algorithms, body scanner algorithms, things like that. Our job is to help create those capabilities that will allow the private sector to ultimately come in and have competitive solutions so that TSA has a huge amount of choices in algorithms. That's what we'd like to do. But Sandia National Laboratories is itself not a private sector company. We're not after profit, and we enable the market to come in and compete. So we're not trying to compete with them. And just a note for everyone, we have had a really good experience with MLtwist. In fact, they've helped us out of a couple of jams because they've been so on top of things, very agile company, and their technology really sort of helped us iron out quite a few errors that we were experiencing. But I want to note that we're not saying that MLtwist is better or worse than a lot of the other partners that we're dealing with. We work with a lot of people, and so we're not ranking them above anybody. But we did have a great experience, and so I'm pretty happy to say that. Next, please, David. Most of you, well, not most of you, but some of you probably know that the algorithm part is the most talked about part of a data pipeline. Your ultimate product is to develop an algorithm. In TSA's case, it's to develop an algorithm that can detect things. But in order to get to that algorithm, you have to collect data. You have to prepare that data. You've got to get that data to the right place. You've got to label that data. That is to say, if you have taken a scan that you're going to use to train your algorithm, you have to label it and say, hey, there is a threat object in this scan, and you got to show where that threat object is. So there's a huge pipeline that leads up to developing that algorithm. And if you ignore building that pipeline, and if you ignore making it robust and comprehensive, you ultimately won't get a great algorithm. So a huge amount of the work we've done is focusing on that data pipeline. Please, David. This is a very busy chart, but the idea is to convey how complex our data pipeline has been, and to indicate to you how errors and risks propagated through that system. So the data pipeline for building detection algorithms for TSA starts with collecting data. So we may go to a laboratory setting, and we may pack bags full of threat objects, things that you wouldn't want on a plane, things that are prohibited by regulation, and you develop a really detailed collection plan. Then you work with people to go and, for example, run bags through that X-ray. And if, for example, you're dealing with explosives, that's a very careful and controlled environment. You have to have a lot of safety regulations in place, and you have to really control how that all works out. So that collection execution is really demanding. Once you do that, you might get an X-ray or a body scan image, again collected in a lab setting, not in a live setting, but in a lab setting, and you get that image, and you need to make sure that, for example, if I've put a knife in a bag, I need to annotate, I need to outline where that knife is. Or if you have a knife on a person, you need to very closely identify which pixels contain that threat object and which don't, because ultimately that's what your algorithm is going to use, that's what your machine learning process is going to use to produce an algorithm that can detect those things. And that labeling and annotation part, it is extraordinarily challenging. And I'll say right up front, that's where we experience a huge amount of risk. If you don't have a pipeline that includes a huge amount of quality assurance steps, if you're not developing a very tight annotation protocol, if you're not watching out for errors all throughout that process, you can end up with data that's no good, and that affects your algorithm. The next thing is we need to get this data shipped to Sandia's database. This data can't just in order for this data to get out to the vendors, we need to have it in a centralized place. We then merge a bunch of metadata. For example, when we do scans with people coming through a laboratory setting, again, never live. When we have people coming through scans doing a laboratory setting, we might look at different body types, a tall person, a short person, a big person, a small person. We need all of those body types. And so we merge the metadata with those scans at Sandia. We then clean up all of that data, and then we get it into our database so that it is searchable. Once we have that, then we get, we've had at least a half dozen vendors on contract at any one time. And over the course of the years, we've had well over a dozen, maybe up to 15 vendors that we've worked with who are developing these algorithms. We've got to get that data out to them. Right now, on one part of our data pipeline, we've been forced to use hard drives, but we've got a situation where we can move to cloud in the future to make that a lot more efficient. So we get that data out to the vendors. Those vendors are then developing their algorithms. And then finally, what we'll do is we'll test those algorithms to see how good they are. And we'll get those algorithms quantified for their accuracy. And then frequently what happens is those same vendors will then say, hey, we'd like to make another collection request. We didn't do well on such and such an item, and we need to do better, so we need more data. What I want to convey about all of this is when we first started, we thought that the data pipeline would be just a collection process. It would just be a matter of circling the threat in a scan and then putting it into a file share. That was naive. The reality is that we needed a very complex set of procedures to handle quality. By quality, I mean, did we place a threat object in the right place in a bag, and did we put the right items in that bag? Because that's something that algorithms have maybe struggled with in the past. We might have struggled with annotation quality. Maybe you needed to annotate. By annotate, I mean draw a 3D box around a particular threat object. Maybe one of the annotators wasn't trained well and they needed to do it quick, so we needed to put in quality assurance processes so we could get that done correctly. And then we needed to put in error checking for how they named a file. Maybe someone gets in a file and then their corresponding partner file for the ground truth annotation was named differently, and we've got to check for those errors. So what we found is we started off with the conception that we would have a simple process, but in reality, we had 75 or more different things that we had to worry about that would create error in our pipeline. And if we didn't manage the error up front, those errors would they would compound and just accumulate over time, so that by the time we got to the data, we would have a mess on our hands. So with that, please, David, next slide. We ended up working with MLtwist on body scanner scans. These scans were collected in a controlled laboratory setting. I want to emphasize there's no collection in a field situation with regular passengers. These are all people who were part of a collection protocol at a laboratory. And we had really tight timelines, and we also knew from our x-ray side of the house how important quality was. And this was also a set of data that we had not really dealt with in depth before. And we ended up working with MLtwist, who had a really flexible enterprise system where they could set up these individual pipelines for us to handle different types of errors, different types of approaches to annotation, and they could easily adjust those same pipelines to handle problems that would come up that we wouldn't even know about until our algorithm developers were working with them. And in doing that, we were able to drive down our all of our errors in that data pipeline, and we actually were able to speed that pipeline up quite a bit as compared to some of our other efforts, such that we dropped, I think we dropped our time from something like several months to a few weeks for getting some data, and we're able to turn around demonstration algorithms for some of our for TSA, so that we could demonstrate these algorithms in a laboratory setting in a very quick amount of time. So we were able to get some quality and speed, but that quality and that speed came because we were able to reconfigure those pipelines and learn quickly. And so the piece I want to emphasize to this audience is you can put together a data pipeline, and planning and forecasting about how it should work is really important, but you also need that agility to change on the fly and change in a way that's reliable in order to get that data pipeline working really well. Next, please. So a couple of things that I want to leave this audience with is, if you're going to be in the business of developing a algorithm which is supposed to detect something somewhere, maybe it's for TSA, maybe it's for something else, you need to think of the entire data pipeline, the data, the processes, the tools, especially the human interaction with that, all of the communications across all of your different vendors. You need to think of that as a dynamic system with a bunch of feedback loops. If you get it right, you're going to get a virtuous cycle. That is, things get better and better and better. And if you get it wrong, you can really go south. So think of it as an entire system. Don't think of it as here's the algorithm and then I've got data somewhere. You need to think of it instead of I've got this complex data pipeline and I need to manage that especially. And if I can do that right, then I can get this algorithm part right. The other piece is that over the long haul, TSA has greatly benefited from owning this data and driving how that data pipeline works. And the more control they had over their data, the more control they had over driving security in a productive direction. So I really encourage people, when they're thinking about working with algorithms, they need to think about owning the data pipeline. Don't just think about the algorithm part, think about the data pipeline. So real quick on some lessons learned. I've talked about it before, but if you don't manage that data pipeline carefully, errors accumulate through your system and you can end up with a bad situation with a bunch of data that's not usable and you've wasted a lot of money. You need to configure that data pipeline to be a bunch of discrete small steps. And when you do that, that means you're able to check for errors and correct errors in all of those little steps in a way that's really quick and really efficient. And then you could put all those steps together for your data pipeline. And that was one of the benefits of working with MLtwist, is that we had all of those steps in little modules, and we reconfigured when we figured out what we were doing wasn't working on the collection side or the annotation side or whatever it may have been. And then part of that is that being able to reconfigure that pipeline when you realize that maybe you started off with an assumption that doesn't prove to be true. You need to be able to re-engineer that pipeline without breaking everything else. And that was a huge benefit of working with MLtwist. And then I would say that the efficiencies of having a really high quality data pipeline in terms of having a really good infrastructure where you can get that data into a really good database, into a really good cloud situation, and having everything work quickly and not having to worry about the infrastructure, not having to worry about those underlying things. The efficiencies for that are much bigger than we originally realized. For example, TSA has not yet enabled cloud for some sensitive information. And when that has happened, that has meant that we can't use the cloud to ship data back and forth, and we had to use these hard drives. And this was on the computed tomography side, not the side that MLtwist is helping us with. The inefficiency involved in that of gathering up data, loading on, doing this manual process of getting on a hard drive and shipping it across the country, making sure it gets to the right place. Hugely inefficient, hugely costly, takes a huge amount of time. It's just not the best solution. And so I would strongly encourage everyone to think about the infrastructure of the data pipeline in addition to the processes. If you have good infrastructure, you're going to make everything work fast. If you can make everything work fast, you can figure out problems early and you can solve those problems early, and you make your whole data pipeline work better. And then finally, I would just encourage a lot of the decision makers who may work for organizations that are more operationally based or they're more policy based. This is typically government organizations. They don't always think of the data first. They think of the operation first, and that's usually pretty appropriate. That's usually the right thing to do. But I would encourage everyone to think about how do I manage my data and control my data? Because the more I do that, the better I do that, the better I'm going to make my operations work. And I think that's something that we've not always seen, and at least until recently. And the more we've seen people pay attention to that data, the better things have gotten for producing great operational outcomes. In TSA's case, it might be better threat detection algorithms. And then finally, what I'll leave you with is if you can work with if you are a data pipeline provider or an algorithm provider or something like that, if you can work with that organization that you're supporting and you can really impress upon them the importance of that data pipeline, you can get a lot of really good things happening where you can get into a virtuous cycle. For example, one of the things that we're going to work with MLtwist on later this year, we're going to collect great data, we're going to get that data annotated well, and we produce an algorithm. That algorithm can be a solid algorithm, but maybe not as high performing as we want it yet, but we can provide that algorithm back to MLtwist, who then uses that to speed up their annotation process. We get better quality, better speed. We then feed that data back into our algorithm. We get a better algorithm that we can then maybe push out to the field or push into a demo. But that same algorithm we give back to MLtwist, who then uses it again to do a quicker, better job of getting that data annotated. So ultimately, what I want to say is if you get that data pipeline right, you can create this virtuous cycle where you can get faster, better quality. You can get both of those things. So I'll pause there, and I believe we're taking questions at the end, and so I'll hand this off, I believe, to David.
Thanks, Andrew. That was fantastic. Thank you for the tee up. I am Dave Smith. It is really good to meet you all. I am CEO, co-founder of MLtwist. I am also the driver, so they wouldn't let me present unless I actually drove the deck. So if you see any driving problems, that's me. So I apologize in advance. And we're going to focus on one of the boxes that Andrew talked about, this data labeling box. We're going to talk a little bit about what's in that box. I did take a look at the registration list before joining the webinar. A lot of you all are computer or some sort of architecture expert. So instead of going into the nuance on 3D data and all the stuff that goes into actually labeling it, I thought what we would do is potentially take a higher level. So first off, want to clarify exactly what Andrew said. None of the information that you're going to see is SSI or has been deemed sensitive. And from an overall agenda point of view, I was thinking, okay, let's talk a little bit about why we're making this whole presentation over this. And overall, it comes down to one concept, which is data quality. So why, right? So the high level of that. And then let's take that box that Andrew had, the data labeling box, and break it out a little bit. What actually gets involved in an AI data pipeline? Are AI data pipelines kind of the same as like regular data pipelines? So let's talk a little bit about that. And then finally, we'll end on a 3D data preparation approach before handing over to Google. So first off, AI has data as fuel. The higher the quality the data, the better the AI performance. So let's talk about that for a second. Dr. Andrew Ng is an AI leader, AI expert over at Stanford. He shared some insights saying that he was able to build a model and get the performance of that model to be the same whether or not he used, whether he used 3 times more OK data than he had good data to get the same performance. So basically, he had a model. He said, okay, if I give you X amount of good data, you're going to perform at this level. And then if I give you 3X amount of OK data, you're going to perform at that same level. So the bottom line is you end up needing 3 times more OK data as good data. We'll talk a little bit about what that actually means. But the summary is good quality data saves you time, costs. From the TSA's point of view, prevents false alarms, allows for accurate decision making. And I also want to press the idea that, okay, if you're looking at 1 megabyte versus 3 megabytes, not that big of a deal. But as you grow, you're looking at gigabytes, you're looking at terabytes, etc. That data starts to become more and more tougher to handle. And if you need 3 times the amount of data, that has a knock-on effect that happens down the road. You also have the concept of bad quality data. So bad quality data, we don't really talk about bad quality data, but the idea is what happens if you introduce data that is noisy to the model. And there's research out there that shows for every 1% you introduce, you have a 1.8% drop in the model accuracy. So you could be in a situation where you are spending money, spending time, getting data ready, you introduce it to the model, and the model's then performing worse than if you had done nothing, right? So these are things that are real. These are things that happen. These are things that are tough to detect. And sometimes you don't even realize you have an AI data pipeline problem until all of a sudden your model starts performing worse. There's all these things that are involved, and this is why high quality data is important. So let's talk a little bit about what goes into high quality data creation. You start out with a scan. So Andrew mentioned this was a test environment, nothing happening in the field. You've got a scan data, and a lot of people think, okay, I just put that data into my AI and I'm good to go. So that's the ETL. Take data, put it to AI, AI learns, continue. But the reality is there's this concept of getting data ready for AI. We're going to call it data preparation. And if you break out data preparation, even at a high level, Andrew mentioned a process of 70-something steps. This is our version of again, 70-something steps. But there's a lot that goes on when it comes to getting data ready for AI. The idea is not to go through every one of these boxes. The idea is to talk about the purple boxes, which MLtwist is very focused on. These are the things that are involved that you can apply technology to. And the goal is you start out with a scan, and eventually you end up with this concept of, and for now we're going to call it a JSON file, but you have a file that describes what's going on in your scan, what's going on in your data. It could be a JSON file, it could be another file, but you are creating a file that describes what is happening in the data you're interested in. For the purposes of this presentation, it's a 3D scan, but it can be a 2D image, it can be a text file, it can be all sorts of other pieces. So let's talk about that little arrow that's in between scan and JSON. That arrow is a combination of a lot of different concepts. So Andrew mentioned the idea that you're able to take your AI and potentially help get that data ready, get the data labeled or annotated for your model. You also have tools. So 3D images require different tools and different annotation capabilities. They're not all built the same. We'll talk about that in a second. We have the concept of people. People are involved. They bring their own expertise, their own judgment. They're able to make those call in those gray areas, and they are able to effectively enhance and improve the quality of the data. You have automation. So a lot of this is powered by automation. What can you do to make the lives of those people easier, to make them better to give them the right tools so that they can do their job in a way that that is good for them and good for the data. And then finally, quality control. Quality control sometimes can be two people working on the same data set, and then you compare them. Ideally, you're going to have some semi-automation in there. You're going to have concepts of, oh, are we detecting, if we're looking at a scan, 2 right arms? Did somebody mess up and accidentally grab a second right arm label? This stuff happens. Did they switch the right and the left arms? There are a lot of things that you can automate on the quality control side to empower the people to go back and find those mistakes on top of improving the quality that they're working on. And AI data tools are something of an interesting ecosystem. So if you haven't heard of Matt Turk, he's an AI thought leader. I highly recommend you look him up, go to his landscape. I grabbed some of the different boxes he had for some of the different modalities of data. And this is, in our estimation, roughly 10% coverage of all the companies that are out there. Different data modalities have different data tools in AI, and you are going to identify tools, and there's not a single MLtwist. So most MLtwist customers have their data flowing to different tools, depending on the modality, depending on what needs to happen, depending on the requirements of the people or the environment. Andrew mentioned there are environments that cannot be connected. There are all these concepts that are out there. So what you end up doing is you end up needing to manage all of this. And on top of that, you have to also think about auditability, about versioning. So a lot of lawmakers in America have talked about what happens when we want to apply some sort of regulation. So we all know about CCPA, California, the Privacy Protection Act. We all know about concepts like HIPAA, different environments. There's regulation on privacy. There's going to likely be regulation on AI and AI data. In fact, Europe just passed their own version a few weeks ago called the AI Act. So on top of all of this, you need to account for where your data has been. And you need to account for things like, were the people working on the data paid a correct wage? Were they subjected to inappropriate content and not given the support or the foundation they need to be able to work on that? Were they put in front of content that they should not have been put into in front of? Is there a way to audit all these questions? And data bias is coming up more and more. Is there a way to understand the bias of potentially the people working on the data in addition to the bias of the data itself? These are all things that are going to need auditability involved. So with that, we'll end on MLtwist, getting data ready for AI. You've got a solution, a hybrid automation of human automation and human intelligence. You take data, push it through to semi-automated labeling, push that through to different tools out there, different teams, different automation for quality control and other types of review, and then you push that through to the company that's building the artificial intelligence, and they're able to continue to work on that. Shout out to the TSA. They have the DICOS standards. So for their security 3D scans, they have implemented open architecture. Open architecture is effectively opening up the ecosystem to companies like MLtwist. We wouldn't be here if it wasn't for the open architecture initiative. We wouldn't be able to work on this type of data. We have DICOS. DICOS is a file format 3D that's built off of DICOM and adds its own security twist to it, if you will. So there's a lot of ability to leverage what DICOM has on working on 3D images in DICOS. And I want to call out that a lot of this is about not reinventing the wheel. Where you can avoid reinventing the wheel, avoid it. There's a lot to do in AI. I also want to call out that with automation, you get improved performance. So the green bar represents the time it takes to ship data back. The blue bar is the time it's taking for people. The red bar is the time it's taking for actually loading, transforming, doing all those pieces in the wheel that you saw. Ideally, that red bar will go further and further to 0 over time. The blue bar will tend to have some sort of limitation on how fast it can go. And the better you are at that red bar, the better you can drive down that blue bar, right? So I'll end with this. Getting data ready for DICOS, you have auto processing, auto batching, sending data through. You have human in the loop. All the things that those people do. It is a tough job. It is a job that you really want to set those people up for success as best as you can. You want to give them the right tools, the right reporting, the right automation. You want to, as much as you can, limit the ability to make errors or have those errors impact things downstream or upstream. You then have automated or semi-automated quality control, and then you have the ability to transform all that data and push it through to a way that entities like Sandia, like their partners, like others, are able to then develop AI models and continue to improve them. So with that, I want to call out that a lot of MLtwist is powered by Google Cloud, and I'd like to hand over to Steve to talk a little bit about Google Cloud. And Steve, I will be your driver for the next session, so just tell me when you need to switch the slides. Over to you.
Wonderful, thank you, David. It's a fascinating project. I love working on these types of technology. So if you can go to the next slide. I just want to spend a couple of minutes talking about Google Cloud and why trust your data with or operating on Google Cloud. So the first thing I just wanted to say quickly is that Google is a data company through and through, and we are fully supporting our public sector customers in their mission set. So we have a dedicated company that just works with public sector. And that operates or supports our customers on the cloud. So Google Cloud operates a FedRAMP moderate worldwide planetary infrastructure. So for missions and customers that have distributed applications or data needs or processing needs, we can operate in a FedRAMP moderate across the planet. And we also operate a FedRAMP high cloud in the CONUS environment. And we do also have the ability to address disconnected mission applications where there is no cloud available. So this is just a real quick map of all of our data centers. We operate in 40 regions with 121 zones, and we continue to build this out. Next slide. So Google was built from the ground up to be a multi-tenant environment to support, again, massive applications. You can think of, the old G Suite, now Workspace, Google Maps, YouTube, you name it. So it has been built as a defense in depth type of architecture. Each domain is discretely separated out with multiple controls. So each region or each section of our defense in depth has complementary controls. So even if one fails, others are there to pick it up. And we're going to drill down a little bit into how we differentiate a little bit as well. Next slide. So this is the main point, two main points I want to get across to y'all on this call, which is you own the data, you own the mission data. Google has no control over it. You define who can get access to it. At no time does Google have any visibility into that. So whether it's enforcing data residency, keeping it, wherever you're operating based on the regulations you are being subjected to, if it, you have to be CONUS, if you have to be in very specific data centers, you set that, and it is guaranteed to operate in that regulation. You can also run assured workloads, which effectively think of it as guardrails as you're going down the highway. You know, the tendency to maybe drift. Assured workloads make sure that nothing changes or gets you out of the regulation compliance. So think of those as the guardrails. Access transparency is everything that happens to your data is logged. And in many cases for sensitive data, you have to have multi-party control over or multi-party approval. So if Google needs to access the data, you have to approve it. So if we're trying to, work on a support ticket, for example, we can't operate or look at that data without your express approval. It is logged, recorded, auditable, all the way through to guarantee that. Everything is encrypted on Google by default. Nothing is stored ever in the clear. You have complete key control should you want it. Google also manages cryptographic key management as well. But at no time do we store anything. So that's data in flight, data at rest, data processing through. Everything is encrypted at all times. And we even take it one step further with confidential computing. So as data moves through the network and it hits a CPU, normally those instruction sets are decrypted, operated on the CPU, and then encrypted on the way out. Confidential computing allows it to remain encrypted even while processing. So you have complete control, end-to-end encryption all the way through. Next slide. So the one thing that's pretty unique about Google is we rely on no third-party software. So any of the third-party vulnerabilities, third-party software vulnerabilities that have impacted a lot of our customers, we purpose build our servers. They're all built by us, for us. They all run this Titan chipset. It's also in our Pixel phones, but essentially it's a chain of trust for the hardware, for attestation. So we build everything ourselves. It doesn't come with video cards. It doesn't come with any unnecessary peripherals. So we want to limit what we have to protect. So it's very purpose built. And that extends to our storage. When we are operating cloud native storage, it's all purpose built, not a third party involved. You can use third party vendors if desired. So again, everything is built to eliminate that risk of supply chain vulnerability. Next slide. And then on top of that, we layer in this zero trust concept, which we pioneered well over a decade ago. Nothing inside of Google is trusted by default. So every user, device, machine, service, and code all has to have an identity and a cryptographic signature to be able to operate. So every person has an identity, the machines, even the code. You can turn on binary authorization to only allow code that's been cryptographically signed, and then data protection as well. So we trust nothing inside the network and protect you at all times. Next slide. All right, so that's like why trust Google Cloud. And then there's the what can I do with it? Okay, so I trust Google Cloud. What can I do with it? So with MLtwist, pipelining, getting that data in is foundational. And so we've spent a lot of time talking about that. Once we get in that data across the bottom, you see pipelines. We start to build up on top of this data. So David mentioned auditability. We also call it explainability, being able to monitor the model performance over time, be able to operate ML ops, which we define as essentially that continuous virtuous cycle that David mentioned, going through, making sure that it's getting better, that you're keeping track of all of the weights and the features and why did something score the way it scored, keeping all that over time as an ML operation, ML ops type of operation. So then I'm going to switch to the top section of this for a second. So Google believes in using whatever tool is the most appropriate for the job. So if that exists on another model, another location, that's fine. We operate first-party tools, as meaning Google design tools, as well as third-party. So whether it be Llama or Anthropic, you name it, there's an entire model garden. We also offer these pre-built, pre-trained models. So all you have to do is provide it the data from someone like MLtwist, and we can use these pre-built, pre-trained models right out of the box to get started. You can also do some fine tuning. So whether it be vision, object detection, translating text, annotating video, speech to text, all of that type of work that you might want to do, as well as your tried and true prediction and forecasting operations that you need to do in AI as well. Will something happen given a set of circumstances? So all of these are pre-built out of the box, easy to use and get started. You don't have to be a ML developer. You can start getting immediate business value. And those will run in either kind of two ways. You can run that in Vertex AI Studio, which is on Google Cloud, or you can use notebooks if you're starting to get into a data science type environment. And of course, all this runs on top of Google's IaaS infrastructure, so all the cloud storage, data warehousing, databases across the board. So it's all integrated and all managed service. So you don't have to spin up data warehouse, you don't have to spin up a database and manage those things. These are all just services. You just point to them and you can easily operate in the cloud. We try to make it very easy. And with that, I'm going to say thank you very much for your time and attention. I appreciate everyone being here.
Alrighty, we can go ahead and move into Q&A. So if anyone has any questions, please feel free to put them in the chat. We have our first question here. If you are able to take advantage of cloud computing resources to scale up your processing capacity, what are the benefits and drawbacks to using ELT versus ETL to prep the data in your lake/warehouse?
So when you think of ETL, right? So it's like ELT, ETL. I think these concepts they're important. I think they're probably better suited for what happens in an environment when you're trying to think of like, I have a lot of data to move. When you introduce human in the loop, it kind of puts things a little bit off the rails. So I'm not quite sure what the question was getting at with the concept of pushing it to the cloud environment, but effectively what I would say is a lot of people today are making this stuff run on their laptops, right? Like a lot of people wrote up a script and like did the thing and then put it in a folder and then booted up some SaaS and upload it to a wizard, like create a project and like that's kind of the reality we see today for a lot of these ETL concepts. And pushing it to the cloud, getting it to work in the cloud is important, whether it's ELT, ETL. The question then kind of becomes, how do you adapt to human in the loop? We stick with the ETL version, so you still need to kind of like mess with the data before you load it. But I hope like at a high level that helps answer that question.
Our next question here is for Andrew. What event triggered you to use an external solution to build your data pipelines?
Yeah, I would say a couple of things. One is we're a research laboratory, so it's just the type of personnel we have. It's not cost effective for us to do that. We would tie up a lot of resources that are meant for other, like basically meant for the right end of the machine learning or the data pipeline. We'd end up tying up a lot of resources to, in data preparation, and that's just not cost effective for us to do. So that was one reason that we went external. The other reason we went external is after a few years of doing this with computed tomography or 3D X-ray, we were doing that with the X-ray side. We realized it was so complex, and that if we were going to really manage this to the quality that we wanted to manage for AIT data, we'd have to do a huge number of steps. We'd have to recreate some stuff. And it was better for us to go with an enterprise solution where someone already had the ability to set up those pipelines really easily. They already had the infrastructure, and that paid off for us. So we could have recreated a data pipeline that had that flexibility in theory, but it was just ludicrous for us to do that given our staffing configuration. So cost effectiveness, and then also someone already had a huge amount of agility and flexibility built into these configurable pipelines, and so that was really attractive to us.
We have another question. How do you evaluate AI performance and when you need more or better data?
I can take that. So if you think of the pipeline, at least I do think this is generalizable, but at least with TSA, you start off with a collection. Let's say you want to detect knives that people might want to smuggle on their bodies to go to an airplane. You collect a set of scans on those knives, and maybe there's a certain. Let's say you collect 20 scans per region of the body. Maybe I've got one that's hidden here, one that's hidden in the center of my chest, one that's on my back, etc. And you develop your algorithm, and maybe your algorithm to be effective at the level that TSA requires, you need to collect double that number in another part of the body. Let's just say you have to collect double that number on, that's my left shoulder. You have to collect double that number on the left shoulder. Well, you're not going to know that until that AI developer, that algorithm developer develops their algorithm. And then what we do is we have a really detailed test and evaluation system where we go in and we test and say, okay, this algorithm works. It finds knives on all parts of the body except that left shoulder. By the way, I want to be clear that I'm being purely hypothetical. And then what we would do is we'd say, you know what, we need to go back and collect more data on that particular region, because the more data that algorithm has, the better off. Now, there's a step that I sort of skipped in there in this specific example. One of the things that MLtwist helped us to do is not just annotate where that knife was in the example, but they also helped us create some metadata for all those scans. They helped us to annotate what regions of the body things were in. So if you have a process that's really fast and a really, you can add metadata at not that much more cost, which then in turn allows us to diagnose what the problems are with algorithms with a lot more fidelity, a lot more precision. And there's been multiple situations where we've worked with algorithm developers where, because we had all of that information, we were able to pinpoint something and they were able to correct it within a couple of days. Hopefully that answers the question.
Andrew, random question for me. Like, when you're looking at this, you've been talking a lot about this from the working on the TSA side, and I know you mentioned originally Sandia is like a fairly broad
Yes.
mission across things like nuclear. How does this? Have you seen this concept like introduce itself in other parts that are non-TSA related? Like, how do people think about this from those points of view? Like, is it like because what's interesting with TSA is like the file scans, 3D scans are pretty bulky, right? So have you seen this also happen where it's like a flood of data, but really small levels, or like just in general, any insights you have on how does this get approached kind of from Sandia's point of view when they're building AI or when they're working on building AI, and like when does it kind of hit that point of, okay, now we got to take this to the next level?
Oh boy. There's a really, really broad set of experiences here. I will say in my sort of view, when I look at some of the other projects I'm involved with and some of the views around me, I'll say thinking of the data pipeline is in very you get a huge amount of data that is on a not necessarily like a large size of data, like the CT scans are really large themselves, but maybe you only have a couple hundred or something. I don't know. But when you have a large amount of data, then yes. And what you see in Sandia is they do actually end up recreating their own data pipelines. Now, a lot of that data is from other, I won't even say what the other projects are, but a lot of it is highly classified. And so you can't necessarily go external. But what you end up doing is they recreate all these pipelines. They end up they ingest the data, and then they have people working on the annotation, and the ones that do it well do treat it as a pipeline where they take their initial algorithm that may have discovered something or that may be able to detect something, and then they put that into their pipeline, and then they use that to sort of create that virtuous cycle where they're ground truthing things at a lot faster and with a lot more higher quality. However, in a lot of situations, and there's other projects I'm on, you end up in a situation where people don't plan for that data pipeline ahead of time, and you run into these massive problems of trying to create quality data. We're working on another X-ray project separate from the TSA work, where we're trying to discover smuggled wildlife products in other countries, and the data collection process is extraordinarily expensive, and I don't know, I think it's probably 50% of our cost in trying to develop these algorithms. So my hope is that people would thinking about things as a data pipeline and figuring out ways where external vendors such as yourselves could go ahead. They would already have the clearances, like you all are going through this process of getting the clearances and so forth, and some of your people have gotten some of that stuff. That would be a huge help to a huge amount of projects in Sandia. Some of them will never go outside Sandia and shouldn't, but a lot of them could. And I would just say that people rediscover the need for having a really efficient data pipeline over and over and over. And I hope that ends someday, and that they just go with an existing solution.
Thanks, Andrew. Sorry, Brittany, I got opportunistic there.
No, all good. We have one more question here. Feel free to continue dropping those questions in the chat, though. What differentiates MLtwist from an open source solution?
That's a good one. So kind of what Andrew was saying. Hey, you have all this, all these different pieces that are out there. In theory, you can kind of build it yourself. In fact, I would say that's probably the majority of a lot of companies are doing. Over time, as Andrew mentioned, the data collection, like the volumes, like there's these other things, and you also have these concepts of regulation starting to creep in. So open source is typically a way to take some code that was out there and use it in your AI data preparation process. But the thing to be conscious of is somebody still will be maintaining it, right? Somebody still will be putting that all together. Somebody still will be having to make it work in the cloud and put in the right environment, and then integrate it with the whatever human or validation components and semi-automate the quality control. So it's not to take away from the idea that yes, like it's a different path. You kind of have software as a service. You have pure services, like I'm going to get a consultant and consult, and then you've got the open source path. So MLtwist styles itself more on the SaaS type of play of being able to put all these pieces together, have it flow, and let MLtwist kind of maintain all of those components and all of that architecture. And that said, there is open source where you can kind of like get somebody to put that all into their own cloud environment and build it and maintain it, and it will be very, very unique to them. Blessing and a curse. It's unique. It's also bespoke. That person moves on, all those things. But I hope that helps, Brittany. It's a good question.
It's definitely that's building the bespoke things, at least in Sandia on various projects. It is sometimes necessary, but it's hugely expensive. It's most of the time it's not It's not the right choice. It's better to go for an existing solution.
Yeah, and we do the same ourselves. Like, we didn't go out and build a bunch of labeling tools that existed, right? That's not our shtick. We didn't go out and hire thousands of people, right? So I kind of want to re-echo that concept of there are things that if that is your core, God bless, go do. If that's not necessarily your core, maybe have a think about it.
And we have one more question here. How does Google Cloud support companies that want to operate in FedRAMP or DoD environments?
So I think I mentioned we do maintain FedRAMP Moderate across the planet, as well as FedRAMP High in CONUS operations. So we have an entire public sector group that is waiting to engage with you and support our public sector customers. So that is our mission, and we want to help you with your mission.
Thank you. Do we have any other questions?
I did miss the DoD one since I cover primarily federal, but we do also operate in the IL-2, 4, 5 space as well. So I apologize for leaving that customer base.
Thank you, David. I want to thank all of our participants, as well as David, Andrew, and Stephen for being with us today. We hope our webinar has been helpful for you and your organization.